We're now going to start a new topic in 0005, which is matrices and vectors. So beginning a new topic means we need a lot of definitions, and here are the initial definitions. First of all, an m by n matrix, so writing this symbol means m by n, is a rectangular grid of numbers with m rows and n columns. It's important to get that the right way round. The first number, the m here, is the number of rows, and the second number, the n, is the number of columns. A square matrix is one which has the same number of rows as it does columns. So that is a matrix which is n by n for some number n. A column vector with height m is an m by 1 matrix, and a row vector with width n is a 1 by n matrix. And we have some notation for the set of all column vectors. For example, r to the n, written like this, is the set of all height n column vectors whose entries are real numbers. And similarly, we might write c to the n like this to mean the set of all height n column vectors with complex numbers as entries. And finally, if we write m subscript m times n of r, what that means is the set of all m by n matrices whose entries are real numbers. And of course we'd extend that similar notation to complex numbers. M sub m times n of c would mean the set of all m by n matrices with complex numbers as entries. Let's just look at a couple of examples to get the hang of these definitions. First of all, at the bottom of the screen here, this thing is a 2 by 2 matrix. So this is 2 by 2. It has 2 rows and 2 columns. Next, what we have here is a column vector. That is a height 3 column vector. So this thing is 3 by 1. Remember, the first number, the 3 here, tells you the number of rows, and this column vector has 3 rows. And finally, what we've got at the end here is a 2 by 3 matrix. It has 2 rows and 3 columns. We need a way to refer to the individual entries within a matrix, and we do that by using matrix coordinates. So the definition is that the ij entry of a matrix means the number which is in row I and column j. So if we take a look at this example here, then for example the 2, 1 entry, what is it? Well, the 2, 1 entry is 4, right? It means row 2, and here we have row 1, row 2, and column 1. So here the columns are 1, 2, and 3. So in row 2 and column 1, you've got the number 4. On the other hand, the 1, 3 entry, that is the entry in row 1 and column 3, so that's this one here. So that is 3. So when we're talking about a matrix and we don't necessarily want to specify its entries explicitly, for example, if we want to talk about an arbitrary matrix, we'll often use the piece of notation on the bottom here. So when we write this, we say a matrix capital A is, in brackets, little a sub ij. What we're doing is we're referring to the ij entry of capital A as little a subscript ij. So in the case when we were talking about a 2 by 2 matrix, this is what the matrix would be right here. You can see that you've got in the 1, 1 entry is written as little a subscript 1, 1. The 1, 2 entry is written as little a subscript 1, 2, and so on. That notation is used very commonly because it enables us to talk about arbitrary matrices, matrices where we don't necessarily want to specify exactly what the entries look like. So here's an example of when we might want to use that notation. We're going to define a way to add 2 matrices of the same size, and that's called matrix addition, and we're going to define a way to multiply a matrix by a single number, and that's called scalar multiplication. So here's the definition. If we have a matrix capital A whose ij entry is little a sub ij, and we have another matrix B of the same size as A, so that means that A and B are both m by n for the same m and n. And if we have a number lambda, then A plus B is defined to be the matrix whose ij entry is Aij plus Bij. So in other words, to add two matrices, we simply add the corresponding entries. And furthermore, the scalar multiple lambda times A, that's the matrix whose ij entry is lambda times Aij. So in order to multiply a matrix by a number, we simply multiply each of the entries by that number. Let's work through an example just to see what precisely is going on here. So here is an example of matrix addition. We have two matrices of the same size, and that's important. We never add two matrices of different sizes. But here we have two 2 by 2 matrices, and there is their sum, and you can see what we've done is simply added the corresponding entries. So to find the entries of the sum, in the top left here you've got the sum of the top left entries 1 and 5 of the two matrices. So you've got 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8, and the result is the matrix whose entries are 6, 8, 10, and 12, like this. So that's how matrix addition works. And matrix scalar multiplication, like here, again, it simply works element by element. So to multiply the 2 by 2 matrix whose entries are 1, 2, 3, and 4 by the scalar, the number minus 2, you simply multiply each entry by minus 2. So you would get minus 2 times 1 is minus 2 here, minus 2 times minus 2 is minus 4 here, and so on. Finally, on the last slide, we're going to look at some of the properties of scalar multiplication and matrix addition, and we're going to look at a special definition of the zero matrix. So let's begin with some of the properties of matrix scalar multiplication and matrix addition. And because that scalar multiplication, because that addition works entry by entry, it inherits a lot of the properties of ordinary real number or complex number addition and multiplication. Specifically, if you have any two numbers A and B, and if you have any two same size matrices, capital A and capital B, then we have the following three properties. So first of all, if you add the numbers little a and little b and then you scalar multiply that by a matrix A, then the result is the same as working out little a times big A and adding that to little b times big A. So again, this is a familiar property for real numbers or for complex numbers, and it transfers directly to multiplying matrices by scalars because matrix scalar multiplication works element by element. Similarly, if you have a single number little a and two same size matrices capital A and capital B, and you multiply little a into capital A plus capital B, then the result is the same as multiplying little a into A and multiplying little a into B and adding the results. And finally, if you have two numbers little a and little b, then multiplying little a into the result of doing little b times capital A, then that's the same as multiplying the two numbers first and then getting the result and scalar multiplying capital A by that. So these properties have familiar names. The first two are called distributivity properties. And the last one is called an associativity property. I won't go into any further detail of those. I think it's pretty clear why these should be true. If you'd like some more details, you can take a look into the online notes for this section. So final definition then is the zero matrix. So for each m and n, we have an m by n zero matrix, which we write as a bold 0 with a subscript m by n. And that's the m by n matrix, all of whose entries are 0. So as an example at the bottom of the page there, here is the 2 by 3 zero matrix, and that's the matrix with 2 rows and 3 columns, all of whose entries are 0.